Hello, friends. Happy to have you here with me today. We're still having fun in Daniel Liang's Introduction to Java Programming. Today, I wanted to bop over to exercise number 4, which is sum of series. So let's see what they have in the book. It says, write a recursive method to compute the following series. The sum of the series is equal to 1 plus 1/2 all the way out through 10. And it says, write a test program that displays m of I for I equals 1 through 10. Okay, so let's go ahead. Let's get this copied. Let's pop into Eclipse. Now, I don't have a package. I haven't done this one before, so let's make a new package. And I'll call this Chapter 18, Exercise 04. And then we'll go inside this and make a new class, and we'll call the class name Chapter 18, Exercise 04. Come here, little helper. My little helper does not want to be a part of the show today. So exercise 04, we're going to include public static void main so we can run this thing. And so we've got this. Let's go ahead and get started. Make sure that it begins correctly. And it does. And then we'll make sure that it'll stop. And when you're doing things with recursion, it's good to know whether or not you get to that last line. So let's paste in the problem statement. We'll do that up here. And let's just go ahead and make this pop right there. And then, all right, so this did not quite look the way that it was supposed to. Plus 1, 5, is it a half, a third? Yep. So a half, a third, plus plus 1 divided by I. Says write a test program for I 1 through 10. Okay, and then we can just end that comment right. Oops. It is shift, unshift, go. Now, so what I would like to propose is, let's say, let's begin with int number of terms. And let's start out with 2. And so the idea, let's do traditional sum of terms, and we'll pass it number of terms. Okay, so this is where I'm going to think through everything just a little bit. All right, so let's see if we can get this going. Say int sum equals 0 for int index equals, trying to, index equals 1 through index less than or equal to number of terms, and then index plus plus. Okay, so sum is equal to sum plus, our first term is going to be 1 divided by index. So let's slow this down. Let's make this 0. And let's say, all right, let's start out with number of terms equals 1. And then here will come out sum of our series was, and sum. So let's just work through this slowly. Okay, so I'm going to take some notes. So one term sum equals 1. Okay, now let's come up here. Let's make the number of terms 2. So this should be 1 plus 1/2. So you know what? This is going to be a problem. This needs to be a double. And this needs to be 1.0 divided by, yes, that is a double. Okay, let's see. So 2, yeah, let's just do this. Okay, so keeping my little notes going, let's try 3. That's wrong. All right, the reason I say that's wrong, 1, oh, wait a second, that's actually right. 1 plus 1/3, 1/2, well, okay, let's, what this should be, all right, so 1 plus 1/2 plus 1/3. All right, so when in doubt, Google it out, right? Internet connection some days, right? 1/8, hey, cool. So now let's try 4. And just copy this. Harmonic series. Let's see if they just give us some totals. No, all right. Can't you just calculate that as a number? Like give it to me as a calculator. So yeah. Okay, how do you edit that? Well, all right. So I'm willing to say, let's just take a look at this. Let's say, all right, you take 2.5 and add it to this. 3 plus 0.5, 3 plus 0.05 is going to be 8. 8 plus 2 is 10. Yeah, I'll take that. I'll say that that's working. So let's go ahead and make our list. Got 5, 6, 7, 8, 9, and 10, right? I'm going to do 11, 12, just to have have some fun with it. Now, let's go in here and let's do let's modify this just a little bit. Let's do for int number of terms equals 1, number of terms less than or equal to 12, number of terms plus, and then we'll open this up and we will close this, Control A, Control I, save it and run it. Now, if I was clever, I would have done something like let's do a printf for %d terms we a series sum of %f for a floating point number, period, and line wrap. And then we can come in and we can do number of terms and sum. And it helps if you don't have numbers in that. Let's save that, let's run that. So 1, 1, hey, this looks great. Let's just grab this. Now, I understand that this is a horrible waste of time, right? Make sure all the numbers match. Except that now I know exactly what it is that I need to go do. Because sometimes on these problems, the math is half the fun, right? So we can replicate some of this work. And so we know what the math is doing now. We know the numbers that we should be getting. Life is pretty good. Life is pretty good. And so now what we're going to do in here is we're going to come in and say, let's call this recursive sum of terms, number of terms. Now, to keep this thing from blowing up, I'm going to say, let's just start out with 1 to 1. Now, still doesn't run yet because we've got to go ahead and create this thing. We'll say, all right. Number of terms. So let's say every time we wanted to return a smaller and smaller fraction, so let's say if number of terms equals 0, return 0. Else return 1.0 divided by double number of terms plus Recursive terms of number of terms minus 1. Oh, that's my own rule that I broke there. So 0 equals, there we go. And so well, pop up here, and then we'll grab this guy, our sum. So our sum, oh, this one here. All right, so hopefully, I don't know, let's just, nothing's blowing up right now. We've done a lot of typing and not a lot of running. Okay, well, that was uneventful. Let's stop at 2 this time and see if they're matching. So let's call this all right. See, it's probably 1, 2, 3, 4, 5. See if that. Let's take another space off. Okay, yeah, all right. Now let's just get greedy. You know, throw caution to the wind. And what we're seeing is it's actually getting us the same numbers all the way through. So that makes me very happy. So I'm going to go ahead and grab this. And I'll pop that down here. Save that. And yeah, basically what I did was I thought through, okay, how did we do this with the whole concept of going through the Fibonacci or the factorial exercise? How can we then repeat that and do that here with these? And so I actually had to work through the factorial exercise twice. The first time I did it was just following the example. And then the second time I did it, I used the recursive definition. And then I suppose the third time I did it was with big integers. So I've actually worked through that problem 3 times to kind of have an image in my head. And that's how I was able to come up with this key little sequence right here, the recursive definition. But anyway, that was how I was able to do that. So with that, hey, I'll tell you what, let me just show you right quick. Git add dot, git commit dash m, added chapter 18, exercise 04, code, and git push. And when things are going well and your network connection's strong, it should be relatively straightforward and relatively painless. However, today, network connection is a little bit strong, got a few things going on, and so, well, yep, can't resolve it, just try it again. I might have lost my network in the process. We have a thunderstorm outside, and so that causes our connection here at the house to get a little wonky. So third time was the charm, got it all pushed up there, but no, recursion is fun. We're not saving a whole lot of lines of code. We're definitely not gaining efficiency, But that's not what we're doing. The reason why we work through these fundamental problems is we can quickly and easily know what the right answer is. And so we've got a way to know, hey, are we actually doing the thought process on our recursive algorithm correct or not? So with that, I thank you all for your time, and I hope you have a wonderful day. Here's to pleasant programming.